I hope video 2 was fun. Let's take a look at this new one right now. Today we're going to take a look at graphing derivatives. Graphing a derivative is something you have to be able to do. Basically, we're just graphing the slope of a function. And then remember, that's what f prime of x is. It is the slope of our function right here. So if I want to graph this derivative, now remember this is a line, right? This is going to be very easy. This is a line, okay? So on the one side we have a line. On the other side, we're going to graph our derivative. So since we know that the derivative is a slope, well, I can find the slope of my line. And it's easy to do. Ready? It has a slope, or right, of 1, 2, 3 over 2. So it's 3/2. So how do we graph that derivative on our derivative graph? Well, everything is basically the same as normally graphing a function. Okay? So on top, remember over here, y values are positive above the x-axis, and we know over here y values are negative, and in the middle, y is always 0. The same thing is true on the derivative graph. Here, the derivative is positive. On the bottom, below the x-axis, the derivative is negative, and in the middle, the derivative is going to be 0. We're going to talk a lot about that in just a few moments. Big lesson for us. So if I want to graph the derivative, we are looking at the slopes. The y values are the slopes. And that's what this represents here. The y values here, don't remember the value of the function, they are the slope at certain points. And if we take a look at a line here, the line is always 2/3 or 3/2 or 1.5. So if I go up on my 0 at 1.5 right here, I'm going to get a horizontal line, because no matter where we go, when my x is 3, for instance, my slope is still 1.5. When my x value is 10, my slope is still 3/2. So we're going to get a horizontal line right there. And that would be the value of our derivative. Now, sometimes another way to look at f prime as being positive. Oops, sorry, wrong one. We typically say here we have a positive slope. And if it's negative, if the derivative is negative, we have a negative slope. And we're going to talk a lot about that, okay? So you really want to take good notes on this one. This is an easy 20 points on your next test. I promise. All right, so let's have some more fun here. Oh no, lines are easy. But what happens when we get to a parabolas? I get it? Parabola. All right, never mind. A parabola. Now, when we get to more curvilicious functions, things change a little bit. Okay? The first thing we want to do is we want to find out where there's a drastic change. Because remember, when we're graphing the slope, we're really looking at, is the slope positive or is the slope negative? Remember, the positive slope on top or the negative slope on bottom. So when I look at the graph, I'm looking for where there's a big change. And that's obvious where the slope is 0, like down here. I know the slope is 0 here. And that's going to be our middle ground right there. So this has a special name for us. It is called a critical number. And it is basically where the slope is 0. We always look for those. Those are what we call critical numbers, because they tell us about a drastic change, something happened in the function. Before my critical number, where the slope is 0, we have a negative slope. And afterwards, we have a positive slope. So that critical number is really going to help us graph this function over here. So, and our critical number is, and we count that, we only worry about the x's, 1, 2, 3, 4, is that x equals 4. So what am I going to do? On my derivative graph, I go to x equals 4. 1, 2, 3, 4. And I put a point. There is my critical number. Right here. Now, from my critical number, I look at my graph. If I go to the left, is my slope getting negative or positive? It's becoming negative. As a matter of fact, it's becoming more negative. So the further down we go, the more negative the slope. So what I do is I start here, and as I go left, I know it goes way negative. It's getting more and more negative. Then if I start my critical number, but this time I go to the right, it gets more positive. So So as we go up, the function becomes more positive, just like your favorite teacher, me. It becomes more positive. Now, if you don't draw it as a straight line for now, that's okay. We're just looking to see if you get the idea. But eventually, we're going to realize that all parabolas basically become straight lines. Very easy to do. So let's try this one. Oh no, it's a horizontal line. This is easy peasy, right? This is pumpkin squeezy. Remember, the derivative is the slope, which in this case is 0. So if I go over to my graph here, where is the slope 0? Oh yeah, on the x-axis. How boring is that? That's just our slope of 0. So there's our derivative graph right here. These are what the derivatives look like. Remember, we said earlier that the derivative is a function. This is a line. This is a horizontal line, a boring one. Y equals 0. Okay? Now, what happens with rational numbers? Okay. Now, with rationals, we approach asymptotes. Asymptotes are another example of a critical number. Now, so you're going to see me abbreviate critical numbers as CNs quite a bit. So a critical number not only occurs where the slope is 0, but also where the slope does not exist. We're going to talk a lot about that later on. So where is my critical number here? Where is my vertical asymptote? It occurs at x equals -2. Now, because it doesn't exist here, remember, this is a D and E at -2. I still have to draw a D and E. So it's still going to be asymptotic at -2. And my asymptote on my x-axis also stays the same. That's not going to change. Asymptotes don't really change from graph to graph. It's just what it does. Remember, here the slope is 0. And then I just look. Okay, so let's imagine. If I start way over here at the left, what is the slope equal to? It's pretty shallow. It's near 0. So what that means is the closer to the x-axis on the derivative graph, the closer to the x-axis on the derivative, the closer the slope is to 0. So what that means is, way over here on the right, my graph is close to 0. So I'm going to start here. Now, as I move to the right, it goes way up to infinity. So remember, it goes way positive right there. It's becoming way positive. So it's going up. So I'm starting here, and it's approaching infinity. So the slope there is approaching infinity. Now, same thing here. The slope is approaching infinity. Remember, whoops, that's a 0. There we go. 2 zeros make infinity, right? Here, the slope approaches 0. So now let's look at the other side. Let's look at over here. Look on the extreme, like over here, this side right here. Here, the slope looks like it's approaching positive infinity. So where am I going to graph that? Well, anything below, remember, is negative slope. We want positive infinity. So it also starts way up here. So I draw an arrow. But as I move over to the right, now the slope is getting shallow, so it's approaching 0. So it's going up, and then it's going down, and it's approaching 0. It'll never hit 0 because there's an asymptote in the way. Doggone asymptotes. It just continues decreasing forever and ever. And there's your derivative. Notice we get another rational function. Algebraically, there is a relationship between these two. We're going to talk about that later on. All right, we have 2 more to do. All right, my favorite graph ever. It's so cubed. So let's go ahead and graph this one. Now remember, this is a curvilicious function. So really what you're looking for is, again, are those critical numbers. I have a critical number here. Remember, I'm looking for my critical number. Then in this case, where the slope is 0 or D and E, we're going to write that out a lot in here. The slope is 0 at, it looks to be at 1, and over here there's a critical number, and at 1, 2, 3, it looks to be at 3. So I'm going to graph to my 2 critical numbers, x equals 1, 1, 2, 3. Notice these are where the slope is 0, and I put that on my derivative graph where the slope is 0. Now I kind of like to do a little dashed line here. These are not asymptotes, these are just going to help me graph it. If I start over here As I go towards the left, what happens? The slope gets bigger, right? The slope is increasing here. I should write that. The slope increases here. So from here, if I go to the left, the slope has to go up. Because remember, positive slope is going up, negative slope is going down. And because it's going up, like a disco duck, I know my graph is going to go up, like so. I'm not worried about the inside part yet. Let's worry about over here. Over here, the slope is also increasing. It's becoming positive. So again, over here, it's going to become positive. And now I worry about the inside. Here we have a negative slope, or the slope is decreasing. So that means it's below the x-axis. But notice, the slope goes from 0 to 0. So it starts here, goes down, but it goes back to 0. That's a tricky one right there. All right, so take a look at that. All right, last one. Are you ready? Remember, we're graphing the slopes. Oh no, we're going to get triggylicious with it, okay? We've got to do some trig stuff. So sorry. All right. So here we have a 45-degree line. Here we have a 60-degree line. We have to find their slope. So how do we find slope? Let me teach you guys something. Let's say we have delta y over delta x. That's slope right there, right? So if I look at a triangle, if this is my line right there, this is my delta y, this is my delta x. That should look familiar. I can look at the tangent of that angle. Well, the tangent of this angle is delta y over delta x. Aren't those the same? Yeah. So therefore, we can say that the slope is the tangent of the angle. And by the way, that is why we call it a tangent line. If I have a function at if I'm looking at a tangent line, the change in x and the change in y is the slope of that line. Why we call it a tangent line. Interesting facts. So right over here, if I want to find the 45 degrees, but be careful, I can find the tangent of 45 degrees, which we know is 1. But be careful, the slope here is negative, so you got to be really careful, right? There's my slope. However, our slope here is going to be negative 1. So I go to the graph. Remember, my slope is negative here at negative 1. Now I'm going to draw, be careful, I'm going to draw an open circle there. We'll talk about y in a second. There's my slope at negative 1. And then I want to find the other one. Well, what is the tangent of 60 degrees? Well, that is the square root of 3, which is a little bit above 1. Okay, so right around here, funk soul brother. And there's my line. It's straight because they're lines. Because remember, the slope is positive up here. And there's our graph. Now, why is this right here open circles? Because look at the function right here. This is not differentiable. There's that corner there, right? So therefore, no slope here. So I have to keep these open circles right there. All right, so I hope you guys enjoyed this video. I know it was a lot today. I apologize for that one, but this was a lot. I appreciate you guys. Thank you.